My name is Camila Kobler, and I, along with Meng, Andrew, Darren, and Jocelyn, are analyzing and redesigning an electric can opener. An electric can opener is a mechanical device that is used to open cans. The can opener holds onto the can and rotates it while cutting open the top. Some designs have automatic shutoff and features which prevent the top of the can from falling into the can itself, and most can cut different sized cans. The typical electric can opener is split into three parts: the housing, which provides the structure of the can opener and protects the components within from outside elements; the transmission, which translates power from the motor into torque to rotate the can; and the cutting mechanism, which is typically fixed and slices open the top of the can. The estimated annual production is 75,000 units. The primary customers are adults who use canned foods regularly. They benefit from the convenience and speed of an electric can opener. The secondary customers are elderly people. They are more likely to struggle with using a manual can opener and would benefit from the ease of use, reliability, and safety of an electric one.
In this slide, a detailed view is shown on how each part is located within the assembly. On the top right side, we have the blade subassembly, which houses the blade itself and the magnet, along with some other structural components. And on the left side, we can see the transmission system and the front and back cover of the main assembly. In our fast diagram, open can is identified to be the task function for the electric can opener. And in order to do that, two basic functions, detach top and control movement, is required. The top is detached by puncturing the top and increases the opening. For control movement, we need to secure the can and align the can. Under assure dependability, we have prevent injury and increase stability. To assure convenience, we would increase the speed of the can opener and reduce the force required to operate it. We can enhance the product by separating the lid of the can and increase the portability of the can opener. Separate lid is achieved by holding the lid and lifting the lid. And finally, to please senses, we will reduce the noise of the can opener. For sequence 1, we can see the blade subassembly is assembled and attached to the front cover first. The motor and gears are attached to their shafts and then placed onto the front cover. The back cover is added last to secure the transmission system. As for sequence 2, the blade subassembly is assembled after the transmission system.
When comparing the advantages and disadvantages of each assembly sequence, we can see that the primary differences have to do with locating parts, fastening, or joining, and the ease of testing the subassemblies. Sequence 1 has the advantage when locating parts because it doesn't require the handler to rotate the unit as often when adding pieces. Sequence 2 must be moved several times for the handler to be able to access different parts of the unit. It also received a low score in ease of fastening because some components must be held in place before inserting another part. For example, the blade and plate must be aligned with a hole in the front cover before the pivot can be installed. Sequence 1 allows more testing of subassemblies because some of them are nearly fully assembled before attaching to the main unit. In the function component mapping matrix, the subassemblies can be identified as clusters of functions. The primary function of the blade housing is to secure and align the can, but the blade also serves to puncture the lid. The transmission subassembly is responsible for transmitting the motor torque, which reduces the required input force from the user when rotating the can. The covers and other components fulfill the remaining functional requirements. The bill of materials shows the parts required for assembly and the estimated costs per part. Prices were estimated under the assumption that 75,000 units would be produced annually. Most parts are machined or injection molded, but the blade and plate are manufactured with sheet metal processes. We decided to order the gears and motor instead of manufacturing them because it was more cost effective. Their prices are reflected in the material costs column.
Every part is functionally important. The blade subassembly is required to cut the can, the transmission subassembly is required to provide the force to open the can, the motor is required to power the device, the front and back cover are required to house the inner components and protect them from the elements or moisture that may be present in the kitchen. The motor is the most expensive component, but it is standard and so it cannot be redesigned despite appearing in the high section. The gears are slightly expensive due to the fact that they are made of steel to increase their lifespan, but if a cheaper model was desired, they could theoretically be replaced with aluminum in exchange for a shorter time span or lifespan. For both customer groups, the can opener punctures the top, increases opening, secures can, aligns can, prevents injury, increase speed, reduce force, hold lid, and lift lid. For the secondary customer, we increase stability, reduce noise, and increase portability for the comfort and ease of use for the secondary customer group. The modules are the front and back cover because changes are necessary to made for these two parts in order to satisfy the functional requirements for the secondary customer. The front and back cover are responsible for increasing stability, reducing noise, so they need to be changed. And the back cover is primarily determines the portability of the whole can opener.
Using a differentiation table, we were able to come up with several modifications to the front and back cover modules that make the can opener more suitable for the secondary customer group. The front and back cover modules feature a wider base, which improves the stability of the overall product, making it safer. Both covers were made thicker, and their material was changed from ABS to mass-loaded vinyl, which has sound-reducing properties. This helps reduce the overall operating noise of the can opener. Finally, a handle was added to the back cover, making the can opener easier to pull out, move around, and store away. This view of the CAD shows the common interfaces that exist between the modules and the platforms. The gear shaft as well as the trigger button go through holes present in both variations of the front cover, and the blade housing sits on top of a curved groove that is also present in both variations of the front cover. The only component that the back cover is joined to is the front cover. As both the back and front covers are modules and the back cover is only joined to the front cover, for the purpose of identifying common interfaces, they can be thought of as one module. The original assembly sequence first selects a version of the front cover module before assembling the remaining components. This is undesired, however, as the product is differentiated right at the beginning of the assembly sequence. In the modified product family assembly diagram, variety is added later in the process. The blade subassembly components are assembled first and then joined to a front cover module before the rest of the assembly continues as normal. This delay in differentiation allows assembly of the blade subassembly components to begin before any potential orders are placed for a specific variant.